Isaac Newton looked at the cosmos and saw a stable, predictable clockwork. But in 1915, Albert Einstein proposed that gravity wasn't an invisible tether pulling objects together. It was the fact that mass warps the geometry of space and time. While his theory successfully tracked planets and stars, Einstein's equations contained a bizarre mathematical outcome. If you compressed enough mass into a small enough volume, space-time would cave in on itself. Einstein doubted that nature would actually allow such extreme conditions to exist. Carl Schwarzschild calculated the exact rigorous solution to Einstein's theory while serving on the Russian front during World War I. Amid the mortar fire of the trenches, Schwarzschild proved that if mass reached a point of infinite density, a singularity, it would create a boundary called an event horizon from which nothing, not even light, could ever return. This concept of an absolute cosmic trap, where time itself stops, was a mathematical quirk that set the stage for discovering the universe's most destructive physical objects. To create a physical black hole, a star must have enormous mass. For millions of years, the outward energy of nuclear fusion prevents a star from collapsing, but when that fuel is exhausted, gravity wins. Trillions of tons of material come crashing down in a fraction of a second, compressing the core into an infinitely small point. Skepticism about these stellar corpses persisted for decades, until astronomers detected strange high-energy X-ray emissions coming from the constellation Cygnus. Observations of Cygnus X1 revealed a blue supergiant star locked in a tight orbit with an invisible neighbor. This unseen object is actively flaying the supergiant, pulling its outer layers into a glowing, rotating disk of gas that heats to millions of degrees. By measuring the visible star's orbital speed, astronomers determined its invisible partner contains 15 times the mass of our Sun. Confirming a 15 solar mass black hole proved Schwarzschild's math was real, but it also raised questions about even larger energy outputs detected in the distant, early universe. Astronomers eventually identified quasars, ancient, distant objects emitting the energy of 1 trillion suns. To produce that much power, these objects would need to be driven by supermassive gravity engines, millions or billions of times heavier than any star. To see if such a giant existed closer to home, astronomer Andrea Ghez used the Keck Observatory in Hawaii to peer through the thick dust at the center of the Milky Way. Using advanced optics to correct for atmospheric distortion, her team was able to track the movement of individual stars deep within our galactic core. This data plots those stars whipping around a completely invisible center point at speeds of 10 million miles per hour. For stars to move with that much velocity without being flung away, they must be orbiting a massive, concentrated weight. These extreme velocities prove the existence of Sagittarius A star, a supermassive black hole with 4 million times the mass of the Sun, sleeping at the center of our galaxy. Data from the Hubble Space Telescope later revealed that our galaxy is typical. By analyzing the light from distant galactic nuclei, astronomers found that nearly every galaxy they observed hosts a supermassive black hole at its core. The scale of these objects is staggering. The supermassive black hole in the Andromeda Galaxy has a mass of 100 million suns. Its event horizon is so large that the inner planets of our solar system would all entirely fit inside it. This prevalence creates a timing problem. Quasars prove supermassive black holes existed very early in the universe's history, but there is a physical limit to how fast a black hole can grow by pulling in gas. These behemoths appeared far too quickly to have grown through normal feeding alone. One explanation is direct collapse, where enormous primordial gas clouds collapsed under their own weight to create massive black hole seeds from the start, skipping the star phase entirely. The presence of such massive objects so early in the cosmic timeline indicates that supermassive black holes are integral to the development of the galaxies that surround them. Evidence suggests a symbiotic relationship where a galaxy and its central black hole grow in tandem, locked together through their shared evolution. As a black hole feeds, it liberates a tremendous amount of energy, blasting heat and powerful energetic jets thousands of light years into the surrounding galaxy. This heat prevents surrounding hydrogen gas from cooling and collapsing. Because stars only form from cold gas, the black hole effectively halts the production of new stars. By regulating this star formation, black holes act as cosmic thermostats, determining whether a galaxy continues to grow or reaches a point of permanent stagnation. The ultimate proof of black holes manipulating spacetime came from LIGO. This massive observatory was designed to detect gravitational waves, actual ripples in the fabric of space itself, caused by the movement of massive objects. In 2015, LIGO recorded the merger of two black holes over 1 billion light-years away. The collision converted multiple solar masses into pure gravitational energy, sending literal ripples through space that reached Earth 1.3 billion years later. To detect this event, LIGO had to measure a change in distance smaller than the width of an atomic nucleus. The success of the experiment allowed humanity to hear the universe for the first time. From Schwarzschild's wartime calculations to the detection of tremors in spacetime, black holes have proven to be the primary structural anchors of our universe. They are not merely destructive anomalies, but the essential components that make the cosmos as we know it possible.